The second issue is coupled PDEs. Okay. And of course, as I said, if you look at practical problems, there are more problems where you have to couple PDEs than those where you don't have to, where you have only a single PDE. Okay. Very few practical problems where you need just solution of one PDE. Right. Generally, it's a set of PDEs. Some examples most of you are familiar with: Navier-Stokes, 4 coupled nonlinear PDEs, 5 if you have incompressible flow, because then you have to also take the energy equation into account. Okay. Species conservation equations if you're doing reacting flow calculations, n coupled PDEs for n chemical components, and n could be very large, sometimes 60, 70. Okay. Maxwell's equation, 6 coupled PDEs, and then there are a whole bunch of other applications that you can get into. Okay, equations of plane stress, plane strain. If you look at things like electrochemistry, okay, you will have electric fields to solve for, you'll have concentrations to solve for. Okay, so a lot of applications. And in general, for these types of PDEs, okay, or sets of PDEs, the overall convergence depends on how the individual PDEs are coupled rather than the convergence of the individual equations. So your convergence of Navier-Stokes will depend a lot on how well you couple U, V, W, and P, rather than how well you solve the momentum equation itself, one of the momentum equations. Okay, I mean, of course, I don't get me wrong, that of course is important, but generally people find is the coupling, how you do the coupling becomes very, very important. Okay. And the numerical algorithm, of course, dictates that. So there are 2 very basic approaches to coupling, and this is a broad outline of those 2. One is called the segregated solution approach. So what you do there is, so suppose I have a bunch of unknowns, phi1, phi2, phi3. Now, don't think of 1, 2, 3 as nodes. Think of them as unknown number 1, which is a vector itself. So like U component, or velocity component U, velocity component V, and so on. Okay. So individual phis. So one approach is you solve for each PDE separately. Okay. Each one has its own inner iteration. So because it's a large system of equations still, right? So you still have to solve them using inner iteration. And then at the end, check convergence of the whole system simultaneously to see if the system has converged. Now, when you're solving for PDE 1, the solution for these guys are frozen. So when I'm solving for the U velocity, my V and W velocity and pressure are frozen. Then when I'm solving for V, I use the most updated value of U, and then still old values of W and P. Okay? So at each point here, some equations are more tightly converged than others. So in the end, I have to check for the simultaneous convergence of all the equations to see that, okay, I've simultaneously solved all the PDEs. Okay? And if that is the case, then you stop. Otherwise, you have these outer iterations. So this is again very similar to what we talked about for nonlinear equations. You have an outer iteration to address coupling between PDEs. Okay. These types of iteration for it, it's called Picard iterations. All right. The other option is you take the PDEs, all the PDEs combined, okay, and set up this humongous set of simultaneous equations and then solve it in one shot. So suppose I have 1 million cells. So this first PDE is 1 million unknowns. Second PDE is 1 million unknowns. Okay. So basically what I end up getting is 2 million unknowns. But if you now think about your coefficient matrix, instead of 1 million by 1 million, it's now become 2 million by 2 million. So 4 times more, okay, in terms of size of that coefficient matrix. So it quickly grows in size. But that's the idea, that you just blindly treat all the unknowns as one big vector, okay, and you solve. All right. Now the problem there is, of course, a lot of the linear algebraic equation solver, we use ideas of geometry. For example, we say in the Stone's method, we said, okay, you know, this actually represents the value from this node, that node. Now, if you think about a bunch of unknowns which are not necessarily related to the geometry, because, you know, the first 1 million are related to nodes, and then the next 1 million are for those same nodes but a different variable. So the physics has changed instead of the spatial location. Okay, so it becomes difficult. The other problem people run into with that approach is that, think about, okay, I'm solving for velocity and temperature. Okay, velocity may have values of around 1 meter per second. Temperature has values of 1,000. Completely different orders of magnitude of the link coefficients that you're going to encounter in that matrix, which makes the matrix very stiff, poorly conditioned, gives you bad convergence. Okay. So just brute force, you know, just making everything a big unknown vector and solving it is usually doesn't work very well. There, you have to do something smarter than that to make it work. All right. But that's the general idea, solving all the PDEs simultaneously. And of course, in this case, there is only one iteration, which we will call the inner iteration. I mean, you could call it outer iteration too, but basically one set of iterations. Okay. So that's the idea behind these. Now, if the system of equations is nonlinear, you still have to do outer iterations. There is no escaping that. You can't solve nonlinear equations without iteration. Okay, and that is part of the reason why people love this first approach, because they say, well, we're sort of killing two birds in one stone. We are doing outer iterations anyway, and that's going to help couple the nonlinearities also, or address the nonlinearities also. So it's not such a bad thing. Okay, and that is why this approach, even to this day, is a very, very popular approach for solving the Navier-Stokes equation. Okay, but that's something to keep in mind. Let's talk a little bit about the precise advantages and disadvantages of the two methods. So segregated solution approach, the biggest advantage is modularity. Okay, you can easily add additional PDEs without disrupting the rest of the code. So suppose I have an isothermal flow code and I say, well, now I'm going to do heat transfer. I just add an energy equation to it. Okay, it becomes part of a new PDE. That's it. Okay. So very easy to do. Another very nice thing about that is once you add a new PDE, you can also easily turn it off. So you had a flow code, you added heat transfer. Now you say, well, I still want to run an isothermal case and see what happens. You just turn off your energy equation because it's so modular. Okay, and that's it. So it's ideal for multi-physics codes. If I say, okay, I start with a flow code, then I add energy, then I add chemical reactions, then I add plasma, I can keep adding new physics to it. Okay, doesn't mean that the code will always converge, but from a developer's point of view, it's ideal. Okay, each person, if I have 5 developers, 5 people can work on 5 different aspects of the code and then put it all together. Okay. You can utilize available resources. By that I mean, we have talked for 4 months about solving one PDE, solving a set of linear algebraic equations. That's all knowledge we have gained. Now if I say, well, you can't use that anymore because you have coupled PDEs, then we'd say, well, why did we even learn all that? Okay, that's the idea. People have developed these very sophisticated linear algebraic equation solvers over the last 30, 40 years that you get off the shelf now. Okay, I mean, you go to like a DOE site, there they have these libraries called PETC. Okay, PETC has all kinds of linear solvers and preconditioners. If we now say no, we can't use them, then it's all wasted. So this is ideal for that. You can just use those off-the-shelf solvers. Okay, and then the other thing is low memory. You are basically, what you're doing is your total number of unknowns is, that's the number of nodes or unknowns times the number of neighbors. That's the number of, this here is the total number of non-zeros in your coefficient matrix, and then the number of PDEs. The nice thing also is that same matrix that you've allocated, or memory that you've allocated for your matrix for PDE number 1, once PDE number 1 is solved, that same matrix memory you can use for PDE number 2. You don't have to really reallocate a new set of slots or memory. Okay? So it's really nice. Disadvantage is if the degree of coupling between PDEs is strong, then convergence can be elusive. For example, high-speed flows with, shocks and so forth. Chemically reacting flows is another example. Very difficult to converge with segregated solution. If you have strongly nonlinear problems like radiation, it becomes a problem. And then equations of plasma physics, again, because of the strong nonlinearity and coupling between the physics. Okay. So it's all driven by really the complexity of the problem from a physics point of view, that you sometimes have to use coupled solvers. Coupled solvers, so the advantage is, as I said, superior convergence, and sometimes it's a necessity for the aforementioned problems. You can't avoid it, even if you want to. Okay, but the disadvantage is lack of modularity. If you have a coupled solver which solves flow and heat transfer, it's very difficult to turn off the heat transfer and say, okay, I'm just going to run it with flow. Okay, because your temperature unknowns have become part of the whole matrix now. Okay, so it's very difficult to turn things on or off. I mean, the only thing you can do is you can say, okay, I'm just going to set my boundary conditions and the conditions of my simulation such that the temperature remains constant. But that doesn't save you any CPU time. Okay. Very high memory, and you can see it. I talked about this. This is the number of elements in your matrix, and now you multiply it by the number of PDEs squared. Remember I said when you go from 1 to 2 PDEs, instead of 1 times 1, you're using 4 times or 2 times 2, which is basically a factor of 4 increase. Okay, and you will see that when I go through the math a little bit this here. Any questions? So the memory becomes a big issue when it comes to coupled solution. There are some, many CFD codes nowadays offer coupled solution. Fluent offers a coupled solver. COMSOL has a coupled solver, but if you, for those of you who may have used COMSOL, you'll find that it requires humongous amount of memory, the coupled solver. Okay. Any questions? Simple example. All right. Now I mentioned already that just brute force taking all the unknowns here and arranging them and then trying to solve for them is not the way to go. So can we do something better? So I'll just show you one example of how this can be done in a slightly better way. Okay. Now this is a pretty advanced topic, so we'll just stick to a simple system. So here are two Poisson equations I've come up with. Okay. This one, as you can see, depends on psi, and then the psi depends on phi. So they're coupled, obviously. Linear system still. Okay. Classic example would be, for example, if you're solving a coupled thermal electrostatics problem. Okay. This is something, kind of equation you're going to get. So if we discretize it, we know all this already. This is going to be the first equation, your 5-band form. This is your second equation, 5-band form. Okay. If I now use the segregated solver, what I'm going to do is I'm going to solve this iteratively using whatever iterative solver, solve this iteratively, and then put the whole thing within an outer loop. Okay. But we don't want to do that. We want to do something different. So this, you can see, this is the fact that we are solving it in a segregated manner is semi-implicit. Why? Because this guy is treated explicitly. This is basically from the previous iteration. I can't treat it simultaneously. Okay. Whatever frozen solution I have from the previous iteration, that's what I'm plugging into this equation. Once I've solved this, then that solution I'm plugging it in here, not changing it anymore. Okay. So it's sort of a semi-implicit approach, kind of like what we do for treatment of our nodes, that some nodes are implicit, some are explicit. Same idea here. Okay. But what if we wanted to do everything in an implicit way, completely implicit or fully implicit? Okay, so then what I'm going to do is I'm going to transpose this guy to the left-hand side of the equation, write it here. So now my entire equation set is implicit, all unknowns together. Okay. Now that equation here, these two, I can write it in matrix form. Okay. Here is how, and this is pretty easy to see. You have this times that plus this times that. That's your first two terms. Okay. Then in the second equation, I have this times that, and then 1 times phi naught, which is this term. And you go down the equation, you'll see the same kind of thing happening everywhere. Okay. So what do I have here? If you start thinking about it, this is still a 5-band equation. Why? Because I have north, west, east, south, north. But it's now a vector equation. It's not a scalar equation anymore. Okay. If I write this out as a matrix for all nodes, okay, spanning your 2 to n minus 1 and 2 to n minus 1, okay, this is what you're going to get. You're still going to get a 5-band equation of this form, but every element is now a 2 by 2 matrix. Okay, it's not just one scalar number, it's a matrix. And then your output is in the form of a vector. So this is the phi psi. So if you think about now n PDEs, that's going to be a vector of length n at the node k. Okay, this is a vector of length n at the node k minus 1, and so on. Okay, same thing with the right hand side. Here we are getting 0, 0, but you could have the source term for the phi equation and the psi equation right there. Okay. So this is the structure of the matrix that you're going to get when you write it in that form. These kinds of matrices are known as block banded matrices. Okay. Instead of just banded, they're block banded. And you can see the total memory that you need is the total number of non-zeros times n PDE square, because each one of them, for example, I have 2 PDEs here, it's 2 by 2. If I have n PDEs, then it will be n PDE times n PDE, each one of them. Okay, that's the minimum memory you're going to need to at least store the matrix. Let's not even talk about solution. Just to store the coefficients, you're going to need that much size. So that's why it becomes memory intensive. Because if you have 1,000,000 cells, let's say 5 neighbors per cell, so instead of 5 million numbers, you have now 5 million times however many PDEs you're coupling that square. All right? So this is what I was just talking about. So how do we solve such systems? And that's, of course, a pretty tough topic or advanced topic, but I'll give you a simple example. One method, for example, at least for a structured mesh like this, if you have a banded system like that, you can use the ADI method still. Okay? How do you do it? Well, you use what's called a block TDMA solve. Okay? Instead of the tridiagonal solver that you have been using, you rewrite it in such a way that all the multiplications get replaced by matrix multiplications, all the divisions get replaced by matrix inversions. Okay? And what you then have is a block TDMA solver. If you now use the block TDMA solver, you're still going to be doing row-wise and column-wise sweeps. And each time you solve, you get that entire vector of values for all the nodes along the line that you're solving for. Okay? Now, one thing to realize is that one block TDMA solve is far more time consuming than 2 scalar TDMA solves. Okay, so it's not additive, it's much more than that, because now you're involving things like matrix inversion and all that. Okay, so it becomes computationally more expensive per iteration. Okay, if you need one, just contact me. course, you have to pay $1 million, but I'll give you one. Okay. I have a block TDMA solver from a long time ago that I have used quite often. Now, development of other types of coupled solvers is a lot more challenging, and as I said, this is still a topic of research in applied mathematics and computer science. I mean, every day you see new papers in this area. How to do the coupled solution of PDEs. Okay, it's not trivial at all. All right, so let's go over an example, simple example. This is a linear problem. 3 coupled linear PDEs of that form. Okay, so this is basically a Laplace type equation, except it's in vector form. So this gamma ij, this is a tensor, and I've just made up some numbers there. Okay. So these types of equations are found in the simulation of multi-component diffusion, the Stefan-Maxwell equations. Here are the boundary conditions for the 3 phis. So there are 3 phis here, phi 1, phi 2, phi 3. And these are the boundary conditions, 1, 0, 0. So phi 1 is 1, phi 2 is 0, phi 3 is 0 at the left boundary, and so on. Okay, and those are the combinations I've taken. If you write it out, this equation out in expanded form, this is what you get. So you can see they're coupled. There's phi 1 here, phi 2 here, phi 3 here. Each equation has all 3 unknowns. Okay? Still linear. All right. Any questions so far? All right. So now I discretize it, my standard finite difference. Very straightforward. That's what I get, central difference. Okay. So this first index k, remember, now stands for the variable number. So phi 1, phi 2, phi 3. And then ij, of course, is your nodal index. Okay. So for the coupled solution, of course, what I did was I wrote this out in the block matrix form that I showed you earlier on, and then directly used block TDMA plus ADI. Okay, you still have to iterate because ADI requires iteration. You know, you're still treating north and south explicitly, even though you're solving the equations in vector form. Okay, because there's spatial explicit implicit still going on. If you do segregated solution, here is what you do. What you're saying here is that when I solve the first equation, I'm only going to treat phi 1 implicitly. Okay, the other 2 are frozen. They have been popped over to the right hand side of the equation. So these are basically starred values, and they're treated explicitly. So when I'm solving for phi 1, my phi 2 and phi 3 containing terms all are on the right hand side, source terms. When I'm solving for phi 2, phi 1 and phi 3 are all on the right hand side, and so on. Okay, so this is nothing but a simple 5-band form, scalar form, with a bunch of source terms which are basically evaluated based on previous iteration values. Okay, so here you can see k goes from 2 to 3. Here k goes from 1 to 3. Sorry, there's a typo here. This should be 1 to 3 and k not equal to 2. Okay, and then this one goes from 1 to 2. All right, so that's the explicit form that you would use in segregated solution. And I used, because I'm using a ADI here, I'm also using a scalar ADI here. Okay, for both cases. So for the segregated solution, I tried two strategies. The first strategy is where each equation, only one row-wise and one column-wise sweep, that is 2 iterations per outer iteration. Okay, so when I solve these equations individually, what I'm doing in strategy 1 is I'm just going through one row-wise sweep, one column-wise sweep, and then I'm saying, okay, now move over and solve the next equation. Okay, so I'm not solving them completely because I know things are going to change in the outer iteration anyway. And then the other one I used is I said, okay, instead of that, how about we use a residual criteria? So for the inner iterations, how about we use 3 orders of magnitude convergence? What happens then? Okay. Now, of course, this is a linear system, so things should be pretty stable both ways. And then for the coupled solver as well as for the outer iteration, we used a convergence criteria of, or I used a convergence criteria of 10 to the minus 6. Okay. Again, 101 by 101 mesh. I recorded CPU times, and this is what you get. Okay, it's kind of interesting if you start thinking about it. Okay. So here is segregated solution strategy 1. Strategy 1, remember, is one row-wise sweep, one column-wise sweep, move on to the next equation. Okay, and so on. So number of iterations pretty large, as you would expect. Okay. When you use strategy 2, so tolerance criteria, of course, per outer iteration, you're doing a lot more inner iteration sweeps now. Okay. So now the number of outer, so these are, by the way, number of outer iterations. Okay. It goes down significantly. And then when I do coupled solver, this is the number of inner iterations of the coupled solver. So that's the number of ADI sweeps basically we are doing. Okay. So you can see there's a sort of a mix. Now, interesting thing is the CPU. Okay. CPU, even though this outer iteration count is the lowest, the CPU time is the highest. Why? Because within each outer iteration, I'm converging each equation by 3 orders of magnitude. That takes a lot of inner iterations for each equation. Okay. I mean, I haven't counted how many iterations it's taking on an average, but I suspect quite a few. Okay, a few hundred probably. So this number, that's why, even though that's low, the cost per iteration is pretty high, and so the overall CPU time is high. Okay. This guy, notice, is very comparable to the coupled solver, even though this is a segregated solution approach. So in terms of total CPU time, it didn't make too much of a difference, even though it feels like this is not as good as that one. Okay. Now, the numbers I'm showing you here, they're very problem dependent. There are lots of problems where, and people always emphasize this, they say, most numerical analysts will tell you having this low is very good. Okay, and you ask them why. They'll say, well, because there are a lot of auxiliary calculations you would be doing in a real practical problem per outer iterations. For example, you would recalculate your density, viscosity, thermal conductivity, all the transport properties. You, in a reacting flow, for example, you would be recalculating your reaction rates. Okay, those calculations take up a lot of time because you're doing it for every cell in your computational domain again and again. Okay, so if instead of 5,116, I'm doing it, I have 500 there, and that means I'm doing significantly less auxiliary calculations than something like this. Okay, so that's why most people propose, numerical analysts, they're strong proponents of low iteration count, because ultimately what they find is that for practical problems, this number goes hand in hand with the low iteration count. Okay, unless of course you're using a solver which is so bad that the CPU time goes way too high. Okay, so overall iteration count often people emphasize on, okay, which may suggest that even this could be better compared to that one for some problems. Okay, but I think the story or the take-home message I'm trying to send is that it's very, very problem dependent. You can never say that one approach is better than the other. It depends on the types of PDEs you're solving, on the types of auxiliary calculations you're doing, on the types of inner iteration solvers you're using. Okay, so all those factors come into play. So there's very little one can say as a universal rule that this way is better than the other. Generally, people use the coupled solver when they find that the segregated solution is not working. Yeah, Justin.
How do they scale to the segregated versus the coupled?
The scaling in these two cases will be very similar to the scaling of your ADI method. Okay, so number of iterations typically will go up by a factor of 4 if you double the mesh size. So that has to do with, especially here, because this is a direct ADI solver we are using, it will scale exactly as how ADI will. Okay. Now in these two, it's a little bit convoluted, but on the whole, it'll scale like that. Any other questions? There was one other, I think, hand up. No? Yeah.
For segregated, would you have the freedom to use different methods for each PDE, different mesh sizes and everything like that?
Different mesh sizes would bring additional complexity, obviously, because then you have to interpolate variables. I mean, you could do it, but then it would mean, okay, how do I transfer information, and whether that would then finally give you a stable solution or not, who knows? I don't know. Okay, but generally we are talking, I mean, in this framework, we're talking about same mesh for every variable. Yeah.
Okay.
Now, suppose you're doing a fluid structure interaction problem and your fluid domain and structures domain are completely different, then it's a completely different problem we're talking about. Okay. Because there, you know, the coupling between the variables is only at the boundary. It's not node to node, one-on-one mapping. So in that case, you would say it doesn't even make sense to couple the two node, you know, with a general approach. We should do some kind of coupling where we make use of the fact that it's at a surface. Any other questions? Okay, so final slide. These are not very exciting, but those are what the solutions look like. Okay, they look like solutions of standard Poisson equations. Linear problem again, so the solutions are pretty straightforward. So I think that's where we will end this semester, and hope